Okay, so we've seen two mechanisms. They're very, very similar. One has one free radical that is responsible for ozone depletion, and the other has two equivalents of some radical atom X that is responsible. And the book doesn't want to pin this down to just one culprit. It's spreading the love around a little bit. It says it could be chlorine, it could be nitrogen monoxide, it could be bromine, but the answer is it's chlorine. Chlorine is the one thing that we're really worried about. It's the thing that we took action about. You know, not as a country, but as a global entity. We took United Nations action on it. So the question is, how did we get there? All right, let's tell you a story. What if I could generate a molecule for you, and it wouldn't be expensive? I could do this with a reasonable cost. And this molecule is a gas. And that gas is inert. What does inert mean?
It's in abundance, right?
Those two things are tied together. If you are naturally abundant, you are also inert, because if you are reactive, you would be busy doing reactions. So inert means unreactive, okay? But you can be inert and not be natural. You could be a man-made chemical, and therefore you don't have to be abundant. Those two things are correlated, but they're not causal. Okay, so this reagent is inert, doesn't react with anything. We've thrown some acids at it, we've thrown some bases at it, doesn't do anything. Doesn't interact with anything, which means I can store it forever. It won't go bad. And it's very, very volatile. So I can store it as a liquid, a compressible liquid, and it's going to expand really quickly into being gas. And that means in the 1950s and the 1960s and the 1970s, I can generate completely new products that rely on this thing, because it's a compressible liquid that is very, very easy to evaporate, to turn into the gas phase. There's this thing that we say multiple times in Chemistry 1. Evaporation causes blank. Fill in the blank. Evaporation causes cooling. So I could build a self-contained little system where I would pump the liquid through a pinhole and have it expand into a chamber. And that evaporation would cause cooling. And so it would make the outside of the machine that I've invented cold. And then I would capture the gas, compress it back down again, and put it in a loop. I just invented the refrigerator. And it runs off this new chemical that I've just invented. It's a compressible liquid that is highly evaporative and completely inert. So as long as the fridge doesn't leak, it doesn't corrode, doesn't make any of your electrics go bad. In fact, electric is completely safe with electrics. You could put a circuit board into this liquid and it still works. So we end up using it as a surface cleaner as well. And then in the 60s, when the plastic industry explodes, someone says, why don't we take this gas, this liquid that can easily be turned into a gas, and blow a stream of this gas through the plastic as it's being made, and put lots of big open spaces into the plastic. And we invented styrofoam. Styrene is a filmy plastic, but you blow bubbles into it and it turns into styrofoam, packing material that is incredibly lightweight and buoyant and a heat insulator. And so now I have two markets. I have air conditioning, I have kind of PCB stuff that's minor at that stage in the world, and styrofoam. And then it was the vogue at the time, but women and men, but predominantly women, love to have their hair up. And you would spray essentially glue into your hair as a fine spray of lacquer, and it would hold your hairstyle in place. And previously that was an impossible thing to do, but the aerosol can, you put your chemical in the aerosol, and then you put a small amount of my new creation, this new wonder chemical, in the can, and it turns into a gas constantly. And so you don't lose all of the spray, and so because it's a gas now, it's pushing the liquid out of the can. You don't lose all the pressure on the first few sprays, like it used to do with other regular gases, because it's called CFC. The CFC is a liquid, and it evaporates over time and causes a gas pressure inside the canister. And so we have spray cans, and I can put paint in a spray can, and I can put deodorant in a spray can, and I can put, you name it. I can put cheese in a spray can. This thing is fabulous. There couldn't possibly be any downside to it. CFC contains a carbon. That C belongs for the carbon. Carbon is in group 4. How many bonds does it make? 4. Carbon makes 4 bonds. I'm going to make one of them be a bond to chlorine, and I'm going to make 3 of them be bonds to chlorine. This is chlorofluorocarbon. And this is not the only one. There are multiple different types. Oh, you know, you ever heard of dry cleaning?
Mm-hmm, yeah.
Chlorinated hydrocarbons. Fire extinguishers. Fire extinguishers used to be this thing, BCF, bromochlorofluorocarbons. If I replace one of those with a bromine, I don't get a liquid anymore that evaporates. I now get a solid, a powder, because bromine's heavy. And you throw it on a fire and it puts fires out. This is a chlorofluorocarbon, and this is just one of them, because I can change the number of fluorines, I can change the number of chlorines, I can change the number of carbons. They're not all one carbon long, but this is a nice simple one. 1 fluorine, 3 chlorines. Okay. Well, it's been in existence for about 20 years, And people start to worry about it because every time you spray, that CFC goes out into the environment and is lost. It's gas. It's not coming back. It's gone. And it's inert, which means it doesn't react with anything. And if it doesn't react with anything, then it doesn't react with biology. So there's no biological path for this to be degraded. And that begins to become a concern. Now, our book tells us that there was a shock in 1985 when a bunch of British researchers said there's a hole in the ozone layer and it's this guy that's doing it. And I can tell you, because I was alive in 1985, that that is not the case. We knew way before that, way before that. They must just be picking up something that, like, this is the proof of what was going on. But we had known / suspected that CFCs were bad for a full 15, maybe 20 years before 1985. Because I remember as a child in the 1970s reading, there was a little magazine that was science-based for kids. And I remember them just like, doomsday's coming. And this would have been in the middle 70s. Doomsday's coming, and there was a wasteland, an illustration of a wasteland with a spray can. Like, you're killing the environment, people. This would have been in the early 1970s. So to say that it happened in 1985 and boy were we surprised is not true. Some of us are old enough to remember that that's not true. Okay, so this guy it's a perfect chemical. Without it, we don't have air conditioning. Without it, we don't have refrigeration. Without it, we don't have aerosol technology. Without it, we don't have styrofoam. It has all of these uses, and it's completely inert. And why would you be concerned about something that is unreactive and inert? Well, perhaps you should be concerned about things that are so unreactive that biology can't degrade them. We've changed our mind about that now. That if we're going to build anything new, we want it to not last forever. We don't want, they're now called forever chemicals. This guy's, that's the bad atom. Things with fluorine in them, stick around, and there's not a biological use for fluorine, and it's not a good thing. Okay, well, this put into the atmosphere, lingers around for a while, finds its way up to about the same place where, so the ozone is protecting everything below it from ultraviolet. So this guy needs to get to, or perhaps a little tiny bit above where the ozone is. Ultraviolet hits this and splits off, that's an F, one of the chlorines. And that chlorine radical, what is a radical? So it is about the number of electrons. What specifically about the number of electrons?
It's decreased, or it has one of the electrons knocked off of it, right?
Yeah. Yeah, so it has an odd number. So this basically goes back to being a chlorine atom. Going to put little X's for the electrons. It's in group 7. 7 is almost 8, and 8's the magic number in chemistry. And if it could just find an electron from somewhere, then it would satisfy the octet rule. So it's going to rip an electron off something else. And that's a self-propagating chain reaction, because if it rips an electron off something else, then that something else then also has a negative, then it gets to have a negative, an odd number of electrons. This one would go up to even. All right, this then combines with oxygen. Remember, there's a small amount of monatomic oxygen that ultraviolet also splits apart, and it makes the culprit. So the culprit is our chlorine oxide. And the stuff we're worried about gets to the ozone layer, interacts with UV, makes chlorine radicals, and then depletes the ozone with one of the two mechanisms. Our book calls them mechanism 1, when there is only one chlorine, or mechanism 2, where you make 2 chlorines, make 2 of these, and then they collapse down to a chlorine and an oxygen. Okay. Mechanism 2 has to exist, they had to propose it because the amount of monatomic oxygen that's in the atmosphere is limited. Okay, so there are 2 mechanisms, one that involves this one and one that doesn't. But either way, that's the culprit. It's in both. Okay, so let's pretend that the book is factually correct. Because it might have been all the way, 85 seems late, but maybe it's proof. Atmosphere is all the way around the planet, okay? But the planet has poles. It has a North Pole and a South Pole, and it rotates. So we have weather systems, and those weather systems are different depending where you are, because of the amount of distance that you have to rotate in order to get there, okay? And one of the consequences of that is we have polar ice caps. It is cold in the north and the south because, oh, well, I wrote it as a tilt anyway. I don't know that I was purposefully writing it as a tilt. Because it's tilted, only the middle part of the planet gets direct sunlight all the time. Some of this is away, and then some of this is away, and we have seasons. And the further north and the further south you go, the more pronounced seasons become. Really dark at nighttime. They can be completely dark during the full 24 hours, depending on what the seasonality is. Okay, but we have ice caps here. And it turns out that the CFCs congregate. And that's where the damage gets done. And we see a hole in the ozone layer. How would we detect that? How do we know that it's there?
Measure the amount of UV radiation, I guess, or
Okay. Well, coming through?
coming through.
And then by saying, okay. Yeah, I mean, you could put observatories around here and here and here, and you could just look up and you could see, oh, is the ultraviolet getting through at these different places? Yeah. Or we could do the other one, that it's the stretching of the atoms themselves. If I want to say what the ozone concentration is, I would probably use the infrared. I would look at what the infrared signature is, because infrared is how this goes. And of course, by the time we're in the 70s, 80s, 90s, satellites exist. Who are the people that own satellites that tell us what the weather's going to be?
Or organization.
Yeah. It's not NASA. NASA helps put the satellites up there.
Oh, NOAA, yeah.
What does NOAA stand for?
It's the National Oceanic and Atmospheric.
Administration. Yeah.
Is it right? Yeah.
Yeah. Something like that.
National Oceanic and Atmospheric Administration.
Yeah.
Yeah.
So if we had satellites, and satellites could see, and they had infrared sensors, they'd be able to see ozone. And then by the time that we're in the 80s, 90s, we have maps. We have actually like illustrated maps of the seasonal change in how big this little depleted hole is. Now, when it's a hole, doesn't mean it's completely gone, but it means that the amount of shielding that we receive from ultraviolet at that particular location is severely limited. Good news, the stuff here, actually, what do we care about? Where do people live? Almost everybody lives in the Northern Hemisphere, with the exception of Australia and South Africa. Most everybody lives in the Northern Hemisphere. Even India, which is the subcontinent, you see the dip on the map, that's in the Northern Hemisphere. So, this part right here, still good. But the fear is that if the hole has opened because of the amount of refrigerant that has leaked in the 1950s, 60s, and 70s, that if we don't stop it, and we continue in the 80s, 90s, and into the 2000s, then the hole would, doesn't it make sense that that hole would just continue to get bigger? Yeah. And then because we don't understand the system, because it's climatic, it changes during the year. Based large, actually it's kind of complicated. It's not just this chemical meets that chemical makes that chemical meets this chemical. One of the things that we talked about, I think Thursday, was concentration. That there's a lot of gas, but gases aren't close to each other. Gas particles are a long way from each other, and they have to bump into each other in order to make the reactions happen. Unless, I should have practiced. Unless you give them a solid surface. Now if the chemicals get to meet on a solid surface, all bets are off. They don't have to bang into each other. They can condense together. And now I have another catalyst. I have a surface catalyst involved here. So, the hole expands, the hole contracts. The climate is cold and windy, and the sky is full of ice particles. One fraction of so our mechanism is, I have a radical initiation, maybe to make this one, and then I have another one to follow, and then I have another line that follows that, and then I have another line that follows that. One of these could be happening during the cold months, and you build up a concentration of one of the reactants, and then in the warm months, the UV has at it. So to say, oh look, in the summer the hole gets bigger, and then in the winter it heals itself. No, it's not as simple as that. It's you could be building up a concentration of a component for your reaction in one stage of the climate, and then in another stage of the climate, something else happens.
Okay. So let's have a quick look through. And of course,
After they found, which one's which? Arctic, Antarctic, remind me.
Bears and no bears.
Yeah. Arctus, bear. There are bears here, and there are no bears there. If we could have used the word penguins, I don't know what the word for penguin is, but like there are penguins here and there are no penguins there. Here's something that will not be on any test. I kid you not. And this is lost. You cannot even find this on the internet now. It's like a Mandela effect thing. It's like it never ever existed. And I swear this is true.
Oh.
That sea didn't used to be there. It was Arctic and Antarctic. And then there were two possible ways of naming it, and now there is only one way of naming it. It's now Arctic and Antarctic. But it definitely used to be the other way. But that has been eradicated from history. Nobody can remember that. If there's one here, and here looks to be okay, my next thing is I'm going to look for one here. And there is one here as well. It's not as developed, it's smaller. Why would it be smaller here?
Because there's less people?
Probably. There's the word anthropogenic. Yeah. I want to say anthropogenic. It's anthropogenic. Anthropo meaning people, genic meaning created. Anthropogenic problems are man-made problems, and there are more people here and less people there. And given diffusion, given enough time, if I put something if I burn something here, and I put a gas into the atmosphere here, given enough time, the laws of diffusion say that gas belongs to the entire atmosphere. But it's closer. So it's probably that.
okay, let's see what the book says. Let's have a read. So there's still a little bit about mechanisms in here.
Page 44, 45. We've seen everything that we need to see about mechanisms. They were all in chapter 1. Okay. There's a thing called a Dobson spectrophotometer. That's the instrument that they used to decide that there was an amount of ozone missing. Ozone is a gas that is present in small concentrations throughout the atmosphere. The total amount of atmospheric oxygen that lies over a given point on Earth is measured in Dobson units. 1 Dobson is equivalent to 0.01 millimeters of pure ozone at the density that it would possess if it were brought to ground level at 1 atmosphere and 0 degrees Celsius. Yeah, so for gases...
Oh, no, 25 degrees Celsius.
No. For gases, standard temperatures and pressures are 1 atmosphere and 0 degrees Kelvin. For solutions, we can't do solutions at 0 degrees Celsius, so we do them at room temperature, which is 298 Kelvin. 0 degrees Celsius is 273 Kelvin. So on average, the overhead ozone is about 350 Dobson units. And it varies. It can be, in the tropics, they say that number is only 250. And in the polar regions, that number is actually about 450. So the actual concentration, even at the hole, is more distinct than it is out here at the equator. Stuff at the equator, right? Yet the Earth is turning at a constant volume, not volume, velocity. But if you're standing here, you only have to rotate that many kilometers in order to, that's a day, right? Whereas if you're standing here, you have to traverse a whole bunch more. So the climate here should not be the same as the climate there. Plus the exposure, here's the sun. Today the sun is on our right-hand side. Usually we draw them left to right. There's no rule that says that the Earth is on the right of the sun. We get more prolonged warming here. So the concentrations shouldn't be the same. There's no expectations they should be the same because the climate is different. Okay. So on page 39, there's a diagram. And I'm going to show you the bottom part of that diagram. It is this guy. This is the bottom part. And this is at one place. So this is at the North Pole, at the Arctic. And this is Dobson units, and this is time. And we see a decrease. And look at that trend. That trend is, over a short period of time. That's only over the course of a decade, but it is. Actually, is that a decade? Yeah.
2002.
That's probably something climate-wise. It's probably like, hey, it didn't rain that year, or I don't know what did happen in 2002. But look, this is disturbing. This path is telling us that, if you were a student in a first or second year college science class and you were told to predict what next year's value is going to be, we would extrapolate that down here, which is calamitous. So, at some point, so here on this graph, they say that 1985 was the date
when we can actually say that there really was a hole. We need to legislate. Let me see if I've got the date of the legislation.
I was thinking sometime, right after, like when Earth Day was kind of they declared Earth Days.
Mm-hmm. So even in our book it says, scientists discovered the hole, this is page 40, they discovered the hole in 1985, that stratospheric oxygen over Antarctica had been reduced by about 50% for several months each year. So it's a cyclic thing. And they've known that there had been depletion since 1979, and that there was variation from month to month. And they finally, on page 42, they finally blame chlorine. I'm not going to revisit it, I think we have enough.
And evidence. Here's evidence. So our culprit really is this guy, chlorine oxide. And as the concentration of chlorine oxide increases, the concentration of ozone decreases, basically as an exact inverse relationship to one another. So that chlorine monoxide is
definitely our biggest culprit. Okay. There's a couple of questions on 46 I might want to come back to. What do we want to see? So polar ozone holes, 49, page 49. So one measure of the surface area covered by
low ozone shows that the area lies within the 220 Dobson unit contour line for the mid-September to mid-October period as a function of the year. The area grew rapidly and approximately linear during the 1980s. The size of the hole in maximum depletion years, which was 98 and 2006, has been somewhat larger than in the period, though overall there has neither been an overall increase nor a decrease since the early 1990s. Okay, so we intervened and we managed to pause it. I'm looking for the book to congratulate itself and say this is when we stepped in.
Let's go to the internet. When were CFCs banned? All right.
So there's a couple of things here that don't align. If we only knew that there was a hole in the ozone layer in 1985, why did Europe start banning CFCs in 1978? Okay. It cannot be true. Chlorofluorocarbons were phased out globally under the Montreal Protocol, which was signed in 1987 with a total ban taking effect worldwide from January the 1st, 1996.
Specifically following a 1974 study.
That's in the book there, I just haven't got to it yet. So we get this. Montreal Protocol is 1987. And that leads to a couple of years where people say, you've got to give me a little bit of breathing room to find an alternative, because I'm Ford Motor Company, or I'm Train, the AC people, or General Electric, and I make air conditioners, and I sell $3 billion worth of air conditioners every year. And yes, I know it's good for the environment if we get rid of CFCs, but you're gonna take a $3 billion chunk out of my company if you make me stop right now. So, timeline. And again, I do question this timeline because I was alive. Scientists definitely say there's a hole in 1985. For the world to come around and agree to a protocol within 2 years is phenomenal. Okay? This is a sense of urgency. It's really, really cool. And then, yeah, we'll give you 10 years. I'm going to give you 10 years. I'm reminded a little bit here of, oh gosh, it's got to be about 20 years ago now when we banned trans fats from diet. And one of the big burger chains says, I'm going to remove trans fat from all of the food items in my restaurants. It's going to take me 3 years. Really? I could do that overnight, but it took them 3 years because that's how long industry takes to change. Okay, they just couldn't do it overnight. Total ban in 1996. A global ban of that's more comprehensive, that it doesn't just ban the chlorofluorocarbons, comes in 2010. All right, Montreal Protocol, let's have a look. Montreal Protocol on substances that deplete the ozone layer is this is from the United Nations website. The Montreal Protocol on substances that deplete the ozone layer is a landmark multilateral environmental agreement that regulates the production and consumption of 100 man-made chemicals referred to as ozone-depleting substances. ODS, ozone-depleting substance. When released into the atmosphere, those chemicals damage the stratospheric ozone layer, Earth's protective shield that protects humans and the environment from harmful levels of ultraviolet radiation from the sun. Adopted on the 16th of September 1987, the protocol is to date one of the rare treaties to achieve universal ratification. So, it's the 1980s. In 1980, Moscow had the Olympic Games. The US didn't go. Lots of countries decided not to go because Russia had just invaded Afghanistan. Russia and Afghanistan have a border. Okay. The Western world saw that as an invasion. The Russians said it wasn't an invasion, it was a cry for help from the Afghanistan government. History will write it's the correct answer 100 years from now. In 1984, the Olympic Games were in Los Angeles. And the Russians and the Warsaw Pact countries didn't come. So this is Cold War. This is in the middle of the Cold War. Whatever the US did, the Russians did the opposite too. If Russia said something is good, the US would veto it. If America said something was good, Russia would veto it. Every single country in the United Nations said, stop. Let's stop this.
I think that's why it's chapter number 1 in the chapter number 1 and number 2 in the book, is because it's something that everybody can agree on. Okay, now there's a second set.
Because we still have refrigerants, right? I have a car that was built in 1974. Now, it doesn't have its original air conditioning system, but if I wanted to keep a stock car and not diminish its value, I would keep the existing air conditioning system in that car because it would be worth more, which would mean that that car has to run on the old style refrigerant, the old style CFC, which you cannot buy anymore through the big retailers, but you can still get on the grey market for a huge markup. Okay, the old refrigerants. So we banned production of them. We didn't ban use of them. We banned production. And what happens when you ban production is the stockpile of what you've already got, what are you going to do with it? You're probably going to use it until it runs out. And then when it runs out, then you have no option. But there's another set that came after this. So there's a follow-on agreement that takes the H CFCs, where these are hydrochlorofluorocarbons. These weren't deemed important enough to be in the first 100 molecules that needed to be banned, but they were
In a subsequent treaty. Kigali, where is Kigali? What is Rwanda? Yeah. So there was a Kigali treaty that followed the Montreal Treaty. All right. Well, what we want to see is that the whole is
healing itself, and the good news is it's not getting worse. We should look. There are animations. So if there are now computer animations that say if we look from the top down, then the hole is this big, and during the year it flares up to be this big, and then it goes back to being this big, and you can see it breathing in and breathing out and breathing in. But at one point, it might have been yay big, and now it's just settled. Problem being, those molecules, our original fluorinated chlorocarbons, because they're completely inert, they're not going away. There is no other metabolism, there is no other biological process that will take them out of the sky. So we have to wait. We have to wait. Now there's bad news coming in a later chapter when we talk about greenhouse gases and the amount of those gases that are going into the sky. But at the time when we banned CFCs, the global economy was still fairly small. In 1987, China was largely still an agrarian communist society. It was not a modernizing industrial consumer nation. It is now. This would be completely different if China had also been involved at the scale that it could be involved these days, and India also is emerging. Everything would be different. Everything would be different. Okay, page 58. We starts to talk about what our replacements are, and one of the replacements becomes these things: hydrochlorofluorocarbons. And a couple of these are numbered. Let's find the one with the number in it. The numbers are mentioned here a couple of times. If you ever go and get your refrigerant replaced at the auto shop, or someone comes to your house and puts the refrigerant in your AC, if you ever call anybody up, they ask, how old's your air conditioner? And they're looking for two sets of numbers. One is it newer than 5 years? Because that's this class of refrigerant. Is it 15 years old? It's the newer, but not newest refrigerant. Or is it 50 years old? Did it come with the house that was built in 1980? Because if it did, then it was using a refrigerant that is now illegal. And they are not allowed to refill, because, they can tell you the name of a guy that will help you do it, but they can't do it themselves. Okay. Temporary replacements for CFCs were employed in the 1990s. This is page 58. Early on, we had HCFCs, hydrochlorofluorocarbons. The most important were CHF2Cl. So this guy up here, CHF2Cl. And that one became known as CFC 22. They all have numbers like this, but this is 22. The most important example was CHF2Cl, the gas called HCFC 22, or just CFC 22. It was employed in air conditioners, in some refrigerants, and used in blowing foams like styrofoam and aerosols. And it has 5% of the ozone depletion of the previous CFCs. So it's not ideal, it's still a depleter, but it is 95% less depleting than previously. Also, we saw one called 134A. I said before, they don't all have to have one carbon. This is called HFC 134A. 134A has no chlorine. Now, you know the satirical newspaper called The Onion? There was a headline in The Onion from 10 years ago that says, scientists find wonderful new solution to the problem that they caused last year. This is a wonderful solution to the problem that they had previously caused. not knowing that they were causing it. But the fact that you're putting this much fluorine into the environment, potentially, every time it leaks, or you release it on purpose, is potentially a ticking time bomb. We don't know what the long-term effect of fluorine is. We just know that nature doesn't like it. There's a couple of things that nature does not like. It doesn't like organic chlorine. It doesn't like organic fluorine. Organic chlorine tends to be antimicrobial. So when you have a leak of a chlorinated organic material like into water, it kills bugs, it kills microbes. All right, well, who cares? You just kill germs. No one cares about germs, except for the little crawfish that live on those bugs, and then the fish that live on the crawfish, and then the bears that live on the fish, and and the wider ecosystem. So this looks like a way forward, although we'll find out. So 134A is widely available now. If you go and get your car's AC fixed, it's probably 134A that's going in. There's another one called 410A that is a mix of both. Not those both. That one was that's a stopgap, that's only temporary. There's another one that is just CH2F2. Okay. And that gets to be 410A. These two together make 410A. Okay, all right. So here's where the book realizes fluorine bad. Page 59. Unfortunately, one atmospheric degradation pathway for some HFCs and for several HCFCs produces trifluoroacetic acid. Okay, let's reset what we know about this. I'm going to do some real chemistry here. That's acetic acid. Organic chemists were going to call this ethanoic acid, but it's acetic acid, it's vinegar. Okay, what do we know about acetic acid? Acetic. A-C-E-T-I-C-A-C-I-D. This is acetic acid. Strong acid, weak acid. This is the textbook example of a weak acid. What does it mean to be an acid? You give me any one of the three. There's Arrhenius, Larry Bronsted, and Lewis. Any definition of what it means to be an acid?
It's a proton, I'm gonna say it wrong right now. Acceptor, right? No, donor.
Donor.
The donor, sorry.
It's proton donor. Which proton is it donating?
H+.
Yeah, but which one?
The one attached to home?
That one. If this is going to be an acid, it splits apart and puts H+ into solution. This is what it means to be an acid. So, in the molecule that is still intact of acetic acid, which is the weakest bond? That bond. That bond is the weakest bond. And because it's weak and that bond is polar, electronegative oxygen, electropositive hydrogen, I have a disparity in electronegativities. is going to break in a heterolysis way. That goes positive, this goes negative. Okay. Now, because it's a weak acid, it means this bond does not break so completely easily that 100% of the molecules split apart and do this. It remains intact somewhat. And we measure that with a thing called pKa. And we don't have to know numbers. We're not going to be doing numbers. But the pKa for acetic acid is 4.8. pKa's for strong acids are zero, close to zero. Okay. If I replace that hydrogen with the fluorine, did I just make it be more acidic or less acidic? Is fluoroacetic acid more acidic or less acidic? That bond is polar. And there's resonance here. I've got movable pi electrons, which means, when you're bonded to something that is itself bonded multiple times to an electronegative atom, that makes this an electron withdrawing group. Okay, so not only is this oxygen pulling electrons away from that hydrogen, this oxygen is pulling electrons away. What's this fluorine doing? Is fluorine electronegative? You betcha, it's the most electronegative atom that there is. So it's also pulling electrons away. Did I just make the molecule more acidic or less acidic by putting a fluorine in it? I've weakened this bond. By pulling electrons away from this bond, I weaken it. If one of the downsides of putting this into the atmosphere is that it makes TFA, trifluoroacetic acid. This is a very strong acid. This is a very strong acid. And do we want acids in our atmosphere? No, probably not. Probably not. So, unfortunately, one of the side effects of putting these multiply fluorinated molecules into the atmosphere is they make trifluoroacetic acid, which is going to come out of the sky and find its way back to the earth, because it's going to dissolve in water. It's going to be acid rain. So I've not fixed one problem, but have not made an existing problem worse, but I've now generated another problem somewhere else, because I now have acid rain. Okay. And we haven't figured out, we really still have not figured out the long-term effect of what fluorines are doing. We just know it's not good. All right, so it then says there are these things called halons. Halon chemicals are bromine containing hydrogen free substances like CF3Br and CF2BrCl. Because they have no tropospheric sinks, they eventually rise to the stratosphere where they are photochemically decomposed with the release of atmospheric bromine and chlorine if there is some present. And one thing that it mentioned in an earlier chapter is that bromine is 50 times worse for ozone than chlorine is. Good news, bad news. Okay. Bromine's very heavy. Hydrogens have a mass of 1, carbons have a mass of 12, fluorines have a mass of 19, chlorines have a mass of 35, bromines have a mass of 80. So if I'm going to make something volatile, I'm going with the top set. I can throw some of these in, but once you start throwing bromines in, chances are these might end up being solids. There was we said early on, bromo, chloro, fluoro, methane, BCF, was a white powder that was used in fire extinguishers. These are heavy. Okay, that's to our benefit. The heavy atoms don't have the propensity to go into the upper atmosphere. But when they do get there, they're 50 times worse than chlorines.
So we have to limit the amount of bromine that can get there.
Okay. Are we aware of what else happened in the market? Okay, so let's kind of finish up with a history lesson. And you're all you're all too young. In the 1980s versus I hope you weren't still writing that. Versus the 2020s. Okay. Life's different. Things are different. Industries are different. In the 1980s, so you know, this. If you think about who are the richest people on the planet right now, none of them are involved in anything that was actually happening here. Google didn't exist. The Google billionaires didn't exist. Microsoft did exist, but it hadn't made any money yet. It's about to. It's about to. Electric cars didn't exist. Telecommunications didn't exist in the way that they exist now. Okay, so our industries are different. The big money industries are different than they used to be. People used to do things differently. They bought groceries almost daily that they would cook immediately. And refrigerators were small. And now food is processed, you buy it in boxes, you put it in your freezer, you microwave it. Lifestyles are different. Let's think. Here are the industries that cause the problems. Aerosols, refrigerants, and I'm gonna say polymers. What I mean here is styrofoam. Okay? Because while the plastic was being made, they blew stuff in there. Okay. If you went to a house in the 1980s, there would be multiple aerosol cans in that house. How many aerosols do you have in your apartment right now, or your house?
I have 3 cans of hairspray.
Well, people still have hairspray. Okay.
That's it.
Mostly it's gone. It's gone to pumps that are hand generated, or we replaced the gas. Now it can't be compressed air, because if you have an aerosol can and it's compressed with compressed air, on the first squeeze, all the compressed air comes out. So they had to find something else, and they went to they went to some blend of nitrogen, it's some nitrogen oxide, which is still bad, but not as bad as the CFCs. Yeah, go ahead and look that up. What is it? What is the propellant in an aerosol? It's not the contents of the aerosol that are bad, it's the propellant.
Okay, so they said primarily hydrocarbons like butane, isobutane, and propane.
Okay.
Common types include liquefied petroleum gas, LPG, or dimethyl ether.
Okay.
Compressed gas like CO2 or nitrogen.
Yeah, so there is a market here for some carbon dioxide, a little bit. It's not that big. But they've gone with hydrocarbons. Okay, this makes them flammable. Whereas only the lacquer was flammable before, the propellant wasn't. Now they both are. But the amount of aerosols that exist has dramatically declined. I have one can of aerosol in my house. It's WD-40. It's under my sink. It's the only thing in the house. Everything else is a squirt bottle that you physically propel the spray out of. That market's not gone, but it's going away. Here we went with the 134A, whereas this was a CFC. This was damaging. And then this guy was a CFC. When was the last time you bought something that had styrofoam in it? So styrofoam has gone out of fashion. So the market for styrofoam has also dramatically dropped. What you have now instead is packing materials, little plastic bubbles. You have, it's a big tube. It's just a big plastic tube, and they blow air into it and then thermo seal it, and you make these bubbles, these blisters. But carbon dioxide. So we have ways of getting by. This technology for aerosols, it doesn't matter. It's not as good as it used to be. If you find somebody who's a hairdresser and is of a particular age, they'll say these cans aren't as good as they used to be. This used to be better. the first spray and the last spray were the same velocity. Nowadays, you get a decay, but hey, we're not killing the environment. Okay.
Yeah. The, not like the actual like outlet of the sprays, like they have a tendency to erode more, I don't know.
Okay. All right.